Hey kids, time for derivatives of exponentials and logs. You know you love exponential and log functions. You know you do, right? Well, maybe you at least love exponents. I'm going to tell you, you're really going to love derivatives of exponents. So I'm going to take you through a couple derivations in this video. First, I'm going to kind of do a graphical derivative of e to the x. So if I asked you to draw a graph of e to the x, hopefully you would do this. And at x equals 0, if I asked you to draw a tangent line using our unit 3a skills, and I asked you to estimate the slope of that tangent line, if I put this on a grid and counted, or even if you can see from here, I hope that you can buy the fact that I say the slope of that tangent line at x equals 0 is 1. Okay, and I could count it and it would, all right, it is an approximate, but if I really zoomed in, I promise you would see that this rise over run was 1. So there it is, right? Up 1 over 1. Slope at 0 appears to be 1. If that's true, then look at the limit definition. Remember, the limit definition of a derivative is the limit as delta x, which we call h, approaches 0 of the function with x plus h in, right? The function at x plus h minus the function all over h. But remember, what did I choose my x to be? Right, I chose my x to be 0. So that's why you see a 0 here and a 0 here. But hey, what's e to the 0? Right? So the definition of derivative of the function e to the x is this. But again, I put in 0 for my, right, for my h. Wait, let me go back for a second. We're saying that that equals 1 at x equals 0, right? The slope of the tangent is 1. Okay? So now I am going to go and do the general definition. And I'm going to do some algebra 2 factoring here, right? Pull out e to the x after I split this up. Remember, you know from your exponential rules that, right, anything to the, let's see, if I have e squared times e to the 4th, isn't that e to the 2 plus 4, right? So I just went backwards with this little piece here, right? E to the x plus h is the same as e to the x times e to the h, and that allows me to factor. I factor out an e to the x, right? So I pull an e to the x out front. That gets rid of that e to the x, because the e to the x divided by e to the x is 1. E to the x divided by e to the x is 1. And there I have my fraction. But remember, this is just over 1, right? So I can split up the fraction this way, multiplication, right? Now I want you to realize that the limit is just involving h, right? This e to the x has nothing to do with the limit. The limit is as h approaches 0. So I'm going to take this e to the x out front. And then, hey, look at the screen, the notes that you took on the screen before. Right? What did we say this is? This is actually the limit as h approaches 0 of e to the 0 plus h minus e to the 0 over h, right, from the screen before. And e to the 0 plus h is e to the h, and e to the 0 is just 1. So using the information from the screen before, what did we say this expression was equal to? This is the derivative of e to the x at 0, right? At 0. What did we say that was, though? 1. So what did we just do here? Hold the phone. The derivative of e to the x is e to the x? I mean, that's crazier than the derivative of sine being cosine. What? This is craziness. Who has not been amazed to learn that the function y equals e to the x, like a phoenix rising from its own ashes, is its own derivative? Oh my Lanta. The slopes on e to the x are described by e to the x. I mean, that's crazy. This quote is not mine. It is this guy, Francois Leonnet, I think, if I'm saying that right. He is loved his chess, this guy. And I can't help but thinking of Harry Potter, right? Phoenix rising from its own ashes. Anyway, that's freaking nuts. Whoa. The derivative of e to the x is e to the x. Now, I want you to get your calculator, and I want you to do this with me. Giving you a moment. Get that calculator. Do this along with me. Ready? In y1, I want you to put e to the x. And then in y2, I want you to ask your calculator. Now, this screen capture is from the older version, right? Deriv. You won't see, if you have the newer version, you won't see Deriv. You'll see this, right? Oops, I need to not be in green. Right, so you're going to put, if you have that version, you're going to put x here, you're going to put y1 here, and you're going to say for all x here. And then do you see what I did here? If you go over here and make your cursor blink and hit enter, I don't know, I can't remember how many times. It blinks on there, you hit it once, you get a thick line, you hit it twice, you get a triangle, you hit it another time, you get another triangle, and then you hit it one last time and you get this bubble. And all that does is slow the graphing down. But if you do this, what the calculator will do is it will graph e to the x, and you'll see it graph pretty quickly. But then this little bubble just slows the graph down to be able to highlight to you that the calculator will find the numerical derivative of the function you put in y1 at every x. And what you'll see is the same graph traced over. Oh my Lanta. E to the x is its own derivative. That's freaking nuts. Incorporating the chain rule, right? So taking the derivative with respect to x of e to the x, right? No stuff, is just e to the x. But the derivative of e to stuff is e to the don't touch the middle, spit out the derivative of the middle. So for example, find the derivative of y with respect to x if y is equal e to the stuff. The derivative of e to the stuff is e to the don't touch the stuff times the derivative of the stuff. Traditional just to put the coefficient in front, right? Pi is a number just a little bit bigger than 3, but it is a number, not a variable, right? Now, what about if I have the derivative of any number to the x? E was a special number, right? We know that the derivative with respect to x of e to the x was just e to the x. And e is a number a little bit smaller than 2, right? Pi is approximately 3.14-ish. E is approximately 2.7 Andrew Jackson window wiper. Right? You remember that? Andrew Jackson, until recently, the worst president of all time, 1828. And then old-fashioned window wipers used to click at 45 degrees, 90, and 45 degrees. But what if my base was any number? Not just 2.7 Andrew Jackson window wiper. A stands for any number. So here's what I'm going to do. You don't have to write this part down. And if you're not interested, skip this part, right? But this is part of what you're in higher level math, the manipulations you're supposed to recognize, right? You don't have to come up with yourself, but you have to recognize what I'm doing. Notice that this expression is the same as that expression, right? E and ln are inverses of one another. So this is just a to the x. So I don't have an equation. I haven't changed a to the x. I just rewrote it. Then I use the property of logs to bring the x down in front. Now notice that I have rewritten myself into a place where I can use the derivative of e to the stuff, right? This is just e to the stuff. How do I take the derivative of e to the stuff? I say e to the stuff, spit out the derivative of the stuff. But think about this. Remember, a is a number, I don't know what the natural log of 2 is. I don't know what the natural log of 5 is. I don't know what the natural log of 15.17 is, but it is just a number. What's the derivative of a number times x? There you go. So, what does this say? What did e to the x ln a really look like? Put the x back here, right? Do this backwards, put the x back, and rewrite. So the derivative of any number to the x is itself, but you must spit out the price you pay. I'm not going to use spit because that goes with the chain rule. I'm going to use the price you pay. The price you pay for not being in base E is you have to multiply by the log of the natural base of A. And it comes from this proof. Now, I am going to add my stuff on my lambda. So this is something you should write down, just like our e to the stuff rule. And really, this is the only rule you really need, right? Because e is a number, and this rule is for any number. The derivative of any number to the stuff is itself, copy and paste, chain rule, spit out the derivative of the stuff, but you also have a price to pay for not being in base E. Natural log of that base. Do you see why this also works for E? Let's use this formula for E. What is the derivative of e to the x using this formula? Well, it's e to the x times the natural log of the base times the derivative of x with respect to x. What is this, though? The exponent that turns e into e is 1, which is why you don't see it in the e to the x formula. And of course, since it was just x, I didn't really have to spit. I was just trying to match this formula, right? Crazy. So let's try some. 2 is not e, so I have to pay the price. So dy dx, or y prime, is copy paste, pay the price. I don't have to spit because this is just an x. In multiple choice, that would probably put parentheses around that because there's so many 2's happening. All right, that one wasn't bad. What about that one? Maybe pause the video and try that yourself, because y, I've thrown a couple things at you. Y is a product, right? If y is a product, to take the derivative of a product, you must use the product rule, but the product rule never changes. The first function times the derivative of the second. So the derivative of the second, I take off into my workspace, and I say, what is the derivative of any number to the stuff? Well, that is itself, pay the price, times the derivative of the stuff. Plus the second function times the derivative of the first. That's about all you would need to do, maybe, right, for a long answer, but you need to recognize that for multiple choice, this could be written in, pun intended, multiple ways. So when you're doing homework, it is worth your time for, maybe not all of them, but some of them, to think about, how might this look in multiple choice? How might there be some other ways I should write this? So for this one, notice that I have a sum, and I've got some things I can put some things in common on both sides of my sum, right? Isn't there an x squared I could pull out? Isn't there a 4 to the 5x I could pull out? And what am I left with here? 5x times ln 4 plus 3, right? That's a possibility. Check this out. This is your Algebra 2 nightmare coming back. Do you see how that happens? Yes, they do that sometimes. You have to know that ln4 might, not must, might be written as 2 ln2. And of course, this 2, right, because 4 is 2 squared, bring it down. And then this 2 is now a coefficient that can match with this coefficient, and I get 10. I'm not saying you have to do that. You don't have to factor either. I'm just saying that sometimes maybe think about how they might write something that you might do this work and then look at multiple choice and go, oh my gosh, I must have done something wrong with the product rule. Nothing looks like, right? But double check to make sure there's not a rewrite. All right. Oops, that's not what I meant to do. All right, what about this one? Uh-oh, y is a quotient, which means to take the derivative, I need to use the quotient rule. Quotient rule never changes, though. O times the derivative of high minus high times the derivative of ho. Oh, the derivative of e to the x is just e to the x. So again, this is pretty good. How might this answer look in multiple choice? Right, well, notice there's an e to the x. They could factor out of the numerator. And this is e to the x times e to the x. So this might look like right? Another thing that is pretty common is in AP sometimes, now this time it was nice to be able to cancel e to the x out, but sometimes remember, don't forget that this can also be written this way, okay? E to the 2x is e to the x squared, right? See the base once with multiple exponents, multiply the exponents. It's handy to remember. All right, so there's our two formulas. But remember, this is really all you need because any number works for any number, just like it. So an e is any number. And the only thing that is different here is the pay the price. You don't have to remember to pay the price if you're in base e because the natural log of e is 1. Now we are going to use this information to find the derivative of logs base e, because remember, logs and exponents are just what? Inverse operations, right? That's why I do a handstand, right? Logs are exponents, handstand, right? Handstand is a, right? Upside down is, I mean, I guess you could say it's a reciprocal and not an inverse, but you know, trying my best. So here we go. What happened? What happened there? I have an equation. So I did e to the y is equal to e to the ln x. That's how I got that. Now I'm going to take the derivative of both sides, right? E to the both sides, take the derivative of both sides. Uh-oh, I'm taking the derivative with respect to x, and what's this? Stuff equals chain rule. No chain rule. The derivative of x with respect to x is just 1. The derivative of e to the stuff is e to the stuff. Spit out the derivative of the stuff. get dy dx by itself. That's called implicit differentiation, right? And there's dy dx. Now, when we did implicit differentiation before, and you had a y in your answer, that was okay. But look at the second line of my proof. What is e to the y equal to? Ah, check it out. Y was equal to ln x was equal to e to the y. So I just replaced y and replaced e to the y. Sorry. I mean, I could have done that too. E to the ln x is just x, right? But that gets me a formula. The derivative of the natural log of x is no logs, right? That's kind of handy. I'm not afraid of logs, but they do cause me some work sometimes. Taking a derivative of a log gets no logs. Now I have a quotient, but I don't have any logs. That's going to come in handy sometime. Notice there's no stuff though. So what happens if I have the stuff? The derivative of the natural log of stuff is 1 over the stuff spit the derivative of the stuff. Now, what if, again, I'm not in base E? The common log is base 10. Or actually, what if I'm in freaking any base? I'm going to do this for base 10, but this could be any base. It's just that base 10 is pretty common, right? That's why it's called the common log. You got 10 fingers, you got 10 toes, right? The metric system, base 10. Hello? So look at me do algebra 2 here. I changed from base 10 to base E. How come? Because I already have a derivative rule in base E. That's why. And again, remember 10 could be any number. I should have really done this with an A down here, and then I would have said ln A. Then notice I just changed a fraction, right? 1 over ln 10, right? This is just a constant. ln 10 is a constant, right? So 1 over ln 10 is still a constant. And then I just use my previous derivative rule. What is the derivative of ln x? Well, it's 1 over x. Hey, there's another pay the price. Pay the price for not being in base E. Now think about this. When it was exponents, you paid the price by multiplying by ln of the base. Logs and exponents are inverses. When you're doing the derivative, not in base E, you have to pay the price, but not by multiplying by the natural log of the base. Dividing. Math is so cool. So even though I showed this in base 10, again, this is any base. I really could have done this for any base. This is your derivative of logs formula, and it works for any base. The log of any base, the derivative, legal base, of course. The derivative of the log of any base is, and pretend I have stuff, 1 over the stuff times pay the price 1 over, or divide by right? You could think of that as another 1 over ln a, right? 1 over u is the derivative of the stuff. 1 over the stuff and 1 over the pay the price, natural log of the base, and then spit, as always, the derivative of the inside. Let's try some. First thing I'm going to do is rewrite this. I'm going to do this problem two ways. As is. That's not just x, it's stuff. And this is my any base, right? It ain't base e. So the derivative is 1 over the stuff, divide by pay the price, right? Or multiply by 1 over. That's my price. Now spit out the derivative of the stuff. But the derivative of the stuff is 1/2 x to the negative 1/2. Now again, think multiple choice. What would this look like? There's a 2 in the bottom. There's an ln 5 in the bottom. There's an x to the 1/2 in the bottom. And there's another x to the 1/2 in the bottom. Right? I want to make sure you know that's not ln of 5x. Oh, so maybe I should put the x over there. Maybe that would be a little bit more clear. Wait, what? Where did that come from? What if this answer was in multiple choice? Would you recognize it? Do you see what happened there? Right? What happened? 2 ln 5, right? This was all separate. 2 ln 5. I could use the bring it up property, ln 5 squared, which is ln 25. Yes, you do have to know your log rules. All right. So here are my derivative rules. Woohoo! Right? Remember, like I said it all along, really you only have two. E is not, right? E is any number. The log of any number. Just so happens that with E, you don't have to pay the price because the natural log of E is 1. So multiplying by 1 or dividing by 1 doesn't change anything. Pay the price when you're not in base E. But derivatives of logs and exponents are pretty sweet. Pretty sweet. Curveball coming, ready? Oh, wait, I'm sorry. I wanted to go back to that one problem and say I was going to do it two ways, didn't I? My bad. Remember when I wrote this as y equals log base 5 x to the 1/2? And I chose to look at x to the 1/2 as my stuff? What if I had used log properties first? What if I said y is equal to 1/2 log base 5 of x? Then when you're taking the derivative of a constant times a function, it's just the constant times the derivative of the function, but notice I don't have any stuff. So what is that? 1 over the stuff times, not the derivative of the stuff because that's just 1, but what do I have to pay the price, right? Wow. So again, this could look like 1 over 2x ln 5. That might be there in multiple choice, but so might 1 over x ln 25. I would say in that case, it was easier to use log properties first, right? I mean, I got to the same place, got to the same answer, slightly faster. All right, sorry that I skipped by that. All right, here, warning, 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 warning. This is a place where you can lose a lot of points. You can give away points, and you don't want to give away points. This is another one of those places where follow-through points don't happen. So I want you to think about the difference in this versus this. When I take derivatives of the first one, notice I have a variable raised to a constant, and I use the power down rule. Over here, I have a constant raised to a variable. That is my exponential rule. Right? This is neither one of those cases. This is not a variable to a constant, and it is not a constant to a variable. You look at your list of rules, and you're like, all the rules I have so far, and I do hope you're keeping a list of rules. Of all the rules I have so far, does that fit any of them? And your answer is no. And I'm not going to make it better. There is no straight up rule for dealing with a function raised to another function. But there is a strategy. So step 1 is to recognize. Because if you try to apply this rule, for instance, I even hesitate to write this down. I'm going to put it in black. It's trying to say like, no, 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 right? So, no, I should put it in red, right? Because red means bad. Oh, I already put that in red. Gosh darn it, right? Red pen. You know, in an education class one time, I took an education class, which are the worst, by the way. I feel like I have to like hold on to my intelligence. Anyway, they told me that I shouldn't use a red pen to grade because when a kid gets a test back and they see red on their paper, it hurts their self-esteem. I was like, what? Why are you thinking kids are so dumb? Right? What? It doesn't matter the color of the pen. It matters the grit, right? So are you going to tell me that if I write an F in green, you're going to feel a lot better? I mean, oh, sorry, MCPS doesn't have Fs. I did in college, but I mean, I give you an E in green, right? Oh my goodness, just nonsense. Anyway, please don't do the following. I've had people look at this and say, oh, well, y prime is bring the x down, in front of the x and subtract 1 from the exponent. Or I've had them, right, they try to use this rule. Or I've tried to use that rule. They try to use that rule and they say, oh, well, that's x to the x times ln x. That's when I want the red pen to make you feel bad. Don't do that. That you are not following the rules. Function to a constant is your power down rule. Constant to a function is your exponential rule. So How do I deal with a function to a function? I'm going to give you a hint. I want this function to come down in front. Who lets me do this? Logs. Problem is, I haven't got any logs, but I've got an equation. All right, so I got to erase a bunch of this nonsense. So, step one was recognize. Function raised to a function. That's step one. Step two, use your properties of equations, which means you can do whatever you want to one side as long as you do the same to the other. Now, after that, what can I do? You have x's and y's, and you don't just have y equals, you have ln y. So step three, use your implicit rules. So I am going to now take the derivative of both sides with respect to x. Take the derivative of ln of stuff. Take the derivative of all x stuff but a product. Using the rule I just showed you, what's the derivative of ln of stuff? Don't have to pay the price because I'm in base E. So, see if you can figure out what I've done here. The derivative of ln of stuff is 1 over the stuff times the derivative of the stuff. No need to pay the price because I'm in base E, which is why I chose to ln and not base anything else, naturally. Then I had to use the product rule, right? And the product rule never changes. It is the first function x times the derivative of ln x, which is just 1 over x. There's no stuff and there's no pay the price. Plus the second function ln x times the derivative of x with respect to x, which is just 1. What do I have to do now? Get dy dx by itself. Usually with implicit, you can stop here. But look back at step 1. You have y explicitly. You started with an explicit relationship. Y is explicitly x to the x in terms of just x. So when you have that case, right, you can replace the y. You may distribute that if you want, but you don't have to. Most times these answers are left like this. Even in multiple choice, you'll see the y kind of out front, the original y out front. All right, crazy, right? So step one, crucial. No follow through points no matter what math you do after x to the x. If you don't do step one, you're not going to get points for anything after. Step two, take the log of both sides, use your log properties to bring the x down. Use your implicit differentiation. Step three. Step four is still really implicit differentiation. Isolate dy dx. And then I need to add here and replace y. Okay, let's try one. Oh, I do need to tell you that the name of this, you should write this in your notes. Logarithmic differentiation. And here's why you want to write that in your notes, because sometimes you will just get a problem like this. It'll just say, find the derivative. Find y prime if y is equal x to the x. Then step one is crucial. But sometimes the problems will say this. Sometimes it'll say, use logarithmic differentiation to. Right? So if you see these words on a test, that's them trying to clue you to recognize, right? That's a clue to our step one. But if you read those words on a test and you try to raise your hand in an AP exam and say, I forget what logarithmic differentiation is, right? Your proctor is a history teacher who knows and who is brilliant in history and knows a ton more than all of us in history, but doesn't know what logarithmic differentiation is, nor should she, right? So you have to get used to some of it. It is important, and I try to make note to you and highlight to you when the vocabulary words are important, right? And that one's important. All right, so let's try. Step one. This is a function raised to a function. ln and bring down. Don't know. I'm kind of like writing a couple steps in one. So don't forget you ln'd both sides. Implicit differentiation. So the derivative of ln of stuff is 1 over the stuff times the derivative of the stuff. Chain rule, product rule. Product rule never changes. The first function times the derivative of ln of stuff, 1 over the stuff times the derivative of the stuff, plus the second function times the derivative of the first. So dy dx is equal to y times all of that stuff. Now, how might this be written? This could be written as cosine x cotangent x minus sine x ln of sine x is one possibility. Oh my goodness. Okay, let's see, they could have written this as cosine squared over sine x maybe. Generally, I think if they can get rid of a fraction in multiple choice, they probably will. But you don't have to simplify much except for this. You do have to do that part for full credit. All right, that was a lot of info in one video, but we got it all done at once. Okay, so there'll actually be 2 homework assignments with this one video, but that's because I tried to break it up into exponentials and then logs. Okay, and then of course you can't do logarithmic differentiation until you know some derivatives of logs, which is why that's tacked on to the end of that. All right, and we'll see you in our live session. Woohoo!